Practice question set number 17. I want to find the units that are the same as magnetic field. In other words, the same as a Tesla. In order to do that, I'm going to write down an equation or equations that have magnetic field in them. There's only two that I can think of for Physics 30. We say F is equal to QVB, and we say F is equal to ILB. Now, in the end, either one of these should get me the correct answer, whatever the correct answer is. Oftentimes what happens if you have more than one equation with that variable in there, there's going to be one equation that's easier to use to get to the answer, but they all should end up working eventually to get the answer. Let's try the blue one up here, F is equal to QVB. Let's rearrange it to solve for B, since that's what we're trying to find here in terms of variables. F over Q times V. All right, so what are the units for F? Well, we know B is Tesla, right? So we want to find what F and Q and V are. That would be a Newton over a Coulomb times meters per second, right? Do you see that? Well, I see two of them with newtons and meters and coulombs and seconds in there, but does it look like that one? Well, let's try to simplify this a little bit and see if we can make it look like either C or D. We say newtons over coulombs. This is the same thing as times seconds over meters, isn't it? Right? We divide by a fraction here. We multiply by the reciprocal. Newtons seconds over coulombs times meters, is that an option? It is. So our answer would be D. Now, let's say that you went to the green one here, F is equal to ILB, and you're trying to tackle it this way because, you know, look, I got 50-50. Which equation is the easiest one to use? Let's say I guessed the wrong one. Let's rearrange that to solve for magnetic field as well. It's F over I times L. So what do we got here? That's a Newton over an amp times a meter. Newton over an amp times a meter. Oh, look, A and B look like they're close there, right? But neither one of them are actually correct, right? If it's Newton over amp times a meter, then Newton times meters over amps can't be right. With the same variables in different places, it can't be right. Same thing with B. Newton over amps times meters, Newton times amps over meters can't work either. So we would right away, even if we didn't know the answer was D, we'd right away cross off A and B. That means that we've got coulombs and seconds mixed in there, no amps. So let's change an amp into a coulomb per second. Newton over coulombs per second, because an amp is a coulomb per second, right? Q over T times meters, which simplifies to newtons over meters times seconds over coulombs, which is, once again, D. Newton seconds over coulombs times meters. Does that make sense? How many people got D for that? Okay, good. Good. 1. A current carrying conductor is this long. It's placed perpendicular to a magnetic field with this strength. During 20 seconds, this many electrons, what's the average magnetic force on this wire, on this conductor? We're going to say F is equal to ILB. But we don't know what I is, so we've got to find it. I is equal to Q over T, right? But we don't know what Q is, so we've got to find it. How are you going to find Q? How are we going to find Q? We know the number of electrons here. It's multiplied by the charge of an electron. 7.00 times 10 to the 19 times 1.6 times 10 to the minus 19 coulombs. Anybody have a value for that? I'll probably make a mistake on it if I find the value of it. What is it? 11.2? And that would be coulombs, which we'll now take and divide by 20 seconds. Gives me 0.56 amps, or coulombs per second, which I now multiply by L times V. Length is 4 times 10 to the minus 2. And the magnetic field is 6 times 10 to the minus 2. Is it 1.34 times 10 to the minus 3? which we would express as what? 1, 3, 4, 3. How many people got that one? Okay, good. Good. All right. Here's some information there. We skimmed through it, right? If anything jumps out as we draw attention to it. Question says, when an electric current of 10 amp travels through the wire, there's sufficient magnetic force to keep the wire suspended against gravity. That's a big word, right? Suspended against gravity. Imaginary thick physics thesaurus. Suspended means balance. Okay. Two forces balance. Clearly one of them is going to be gravity, right? Because it's suspended against gravity. What other force do we have here that's suspended against gravity? F what equals F what? F what equals Fg? Fm, yep. Magnetic force equals, in magnitude, the gravitational force. So we're going to say for this, what do we got? Is it ILB? Yep. I is 10 amps times the length of the wire, which is 0.013 times the magnetic field, which is, oh, that's what we're finding here, right? Let's rearrange this here. B is equal to mg over IL. What do we end up getting when we do that? Who's got that? 6.41 times 10 to the minus 2 Tesla, which we express as ABCD again, 6412. Good there? Is that it? That was all of them?